So let's take a look at Descartes' rule of signs, which helps us to limit the number of potential zeros of a polynomial function by determining the number of positive or negative real roots. So, for example, if f of x is a polynomial function with real coefficients, the number of positive real zeros of f of x is equal to the number of sign changes in f of x, or the number of sign changes minus an even whole number. And the number of negative real zeros of f of x is equal to the number of sign changes in f of negative x, or the number of sign changes minus an even whole number. So let's take a look at this example. We're going to try to find the possible number of positive and negative real zeros of this given function. So we're first going to look at the number of sign changes in f of x. Okay. And that is the sign changes in the coefficients. And so if you have a positive leading coefficient, so positive 4, and then negative 6, that's one sign change. And then we don't have a sign change between the second and third terms, but between the third and the fourth we do. And so there are 2 sign changes in f of x, which means that there are 2 positive real zeros. Or if we take this number and subtract an even whole number, like 2, we get 0 positive zeros. Okay, if we look at the number of sign changes in f of negative x, first, substitute negative x for x. And simplify. So 4 times negative x cubed, negative x to the third is still negative x cubed. And so that's bring the negative to the front, and it's negative 4x cubed minus 6. And negative x squared is the same thing as positive x squared, since a negative number squared is positive. Negative 8 times negative x is plus 8x, and then plus 15. And now the number of sign changes, the first 2 terms are negative, so no sign change between them. 1 sign change from the second to the third term. And that is it. So 1 sign change in f of negative x means that there's 1 negative 0. Okay, and if we subtracted an even whole number, 2, I get a negative 1, which does not make sense as a number of negative zeros. And so therefore there's only 1 of them. Well, let's take this information and summarize it in a table. We have the number of positive zeros, the number of negative, and the number of non-real. Okay, and positive, I had 2 potential outcomes, 2 or 0. Negative, no matter what, there's only 1 of them. And then we have to figure out this third row, the non-real. And so take a look back at what the degree of the polynomial function is, which is a 3 or cubic. And that means altogether, real and non-real, there can be just 3 zeros. And so if there's 2 positive and 1 negative, there's 0 non-real. If there's 0 positive and 1 negative, there are 2 non-real. And take a look at these columns. They should total 3. So what if I then want to find those zeros? So find any possible zeros of this function without knowing any initially. One thing that we could do is use the rational zero theorem. And so we're going to find our p's and q's and then divide them. So p, those are going to be factors of 15, which is the constant, and that's plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. And then factors Q is factors of 4. So plus or minus 1, plus or minus 2, plus or minus 4. And then we divide them, P by Q. Okay, so take your P's individually and divide them by Q one at a time. And so we get plus or minus 1 divided by plus or minus 1 is still plus or minus 1. Continue across, so we'll get plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Okay, and then we'll take each of them and divide by plus or minus 2. Okay, so plus or minus 1/2, plus or minus 3/2, plus or minus 5/2, plus or minus 15/2. Okay, and then we'll do this one more time and divide by 4. So plus or minus 1/4, plus or minus 3/4, plus or minus 5/4, plus or minus 15/4. Okay, well at this point we have many different possible rational zeros, and so it would take a long time to substitute each one in individually into the given function. So I'm going to use my calculator, enter the function in y equals. Okay, we're going to go to our table, but first go to the table setup, which is under second window, and set the independent variable to ask. Okay, and then look at the table under second graph. Okay, and we're just going to start entering these potential rational zeros. So 1, -1, 3, -3, 5, -5, and 15, -15. Okay, what we're looking for is a y value of 0. So far, none of those worked. But continue. So 1/2, -1/2, 3/2, -3/2. Okay, here is 1. This is a real 0, which is a rational number, -1.5, -3/2. So right now I'm going to stop, and we're going to use this known 0 to get another factor of our function. Okay, so our known factor now is x minus -3/2, or x plus 3/2. Our unknown factor, we're going to try to find. And so to do that, we'll put -3/2. In the corner, we'll use synthetic division and the coefficients of f of x in this top row. 4, -6, -8, and 15. Okay, drop down the 4 and multiply 4 by -3/2. And that is -6, and add, and we get -12. Okay, and multiply, let's see, that is +18, and add, so 10. And multiply -15, and add, and we get a remainder of 0. Okay, so here is our other factor, 4x squared minus 12x plus 10. Okay, well, what we need to do now is set this other factor equal to 0, and then we can find the remaining zeros of this polynomial function. Okay, so I'm going to first reduce this equation, divide both sides by 2, and we get 2x squared minus 6x plus 5 is equal to 0. Okay, so a little bit easier to work with. And we talked about how if I want to decide, can I factor this quadratic, or should I just jump to the quadratic formula? Don't forget, you could use completing the square, okay? So you could use the discriminant to help you decide. So d is equal to b squared minus 4ac. I'm just going to do a little quick check. B squared, so that's -6 squared, minus 4 times 2 times 5, and that's 36 minus 40. or negative 4. This tells me that my solutions to this quadratic are going to be non-real. Okay, so there is not an easy way to get them other than to complete the square or use the quadratic formula. So I'll use the quadratic formula. Okay, so remember it's negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. Okay, and b again was negative 6, so the opposite of negative 6 is 6, plus or minus the square root. Okay, this is the expression that we had over here. Okay, that is the discriminant. So negative 6 squared minus 4 times 2 times 5, and divide by 2 times a, which is 2. Then we just want to simplify. So 6 plus or minus, we said that was the square root of negative 4 divided by 4. And remember that a negative under the radical, that's a non-real number. And we can write it in terms of I. So we get 6 plus or minus, the square root of 4 is 2, the square root of negative 1 is I, and then divided by 4. And lastly, if we want to write this in a plus bi form, you'd break this up, divide both of these terms in the numerator by 4. So 6 over 4 is 3 halves, plus or minus. 2 over 4 is 1 half, and then I. Notice that non-real complex zeros come in conjugate pairs. That's the a plus bi, a minus bi, and that is true in this scenario. Okay, so all together, the goal was to first see what types of zeros we would have. And using Descartes' rule of signs, we saw that there are 2 possible options. Okay, option 1 or option 2. And this one we saw there were 2 non-real zeros and 1 negative, and therefore our solutions match what we found with Descartes' rule of signs. Okay, well, one other thing, let's just write out all of our zeros of the given function. Okay, the real zero was negative 3 halves. Okay, the non-real zeros are 3 halves minus 1 half I, or 3 halves plus 1 half I.